You guys pretty good? Anybody pull out any of their fridges or anything like that?
Excuse me.
Yep.
For the test on Thursday, are we gonna have a review for that test tomorrow?
Yes.
And there's gonna be a quiz on this tomorrow too?
Yes.
Okay, thank you.
All right. Again, that reminds me, everyone, as you know from last week, we do have a quiz test this Thursday. All right. That's going to cover everything from our last exam. So all freshwater Gen 1, freshwater Gen 2, reefers, and HVAC. All right. All right. Let's go into HVAC. So the biggest thing with HVAC is your environmental controls. All right. It's your environmental comfort that's going on. That's the only reason we're doing this. All right. And comfort is determined by the couple of things. You have your air temperature. You have your air cleanliness. And we seem to have lost the pen. And we have our air cleanliness. We have air movement. And we have, of course, humidity. All right. The obvious thing here is just, what is the temperature? Everybody always cares about the temperature of what an air conditioner is set at. That's always their biggest complaint, everything else along those lines. Second portion that a lot of people don't recognize is their humidity. And the humidity in the air is a huge problem with what people experience. That's the idea that you're going to be sitting there and you're going to have, when you feel really, really wet on the outside of your body, when you feel damp, everything just feels damp and you just weighed down on everything. That's like that heavy, heavy humidity on you and why it's so uncomfortable. All right. You can have a super cold temperature and 100% humidity, and that's not going to feel at all great. So if you're sitting in a room with 68-degree weather and it feels, would that feel really nice? You don't know about the other conditions here, these 4 conditions. These are different pieces that all make up with air conditioning. Of course, air cleanliness. That's just the filtration of it. All right. And also, you have your air movement. If you have a jet engine blasting you of air conditioning, I don't care if you're standing on the sun, that's probably not going to feel too good. But these are all important on how humans feel. If one person's sitting underneath a vent, they're going to feel colder than someone who's sitting elsewhere in the room because of that air being blown over them and how fast it's being blown over them. All right. So in the past, they've had heating, ventilation, and air conditioning with separate systems. Now it's all going into one, especially as we advance with like heat pump technology. We're having that up in the north. Usually, what we'll have is temperatures ranging from 66 in the winter is usually what the air temperature, nice, depending, and then 78 in the summer. Air cleanliness is the removal of odor, dust, pathogens, site specific. So you can have like really, really heavy air filter and filtration systems if you're in like a hospital. If you're in a surgery room, you're not going to want any viruses that are going to be traveling from other rooms to be going into someone who's under surgery. And then again, air movement is always big. How fast you're changing it out, how many times you're doing air changeouts. So you look at, how many times you're going to be in a room, and being in that room, how many air changeouts you're going to have. How many times is the air going to be brought in and it's completely fresh air? All right. And then, of course, we talked about humidity, and there's two different levels of humidity, relative and absolute. So with humidity, you have absolute humidity, and that's the amount of water in pounds or grains. And 1 pound is equal to 7,000 grains per pound of dry air. All right. So at a given temperature, there's a maximum amount of H2O that a pound of air can hold. And then relative humidity is the percentage of the maximum H2O at a given temperature actually present. So when you hear someone talk about, oh, what's the humidity today? They're talking about the relative humidity, the percentage based. All right. With absolute, they're talking about the numerical, how many grains of water is in a pound of dry air. All right. Does that make sense to everyone? Okay. So we have some infographics here. Relative humidity changes as air temperature changes, even as the absolute humidity remains constant. All right. So if we look at what we have here, we said on the last slide, W is your absolute humidity. So here's 3 examples. All 3 are at different temperatures. All right. But they have the same absolute humidity, each one of them. So the W max, the max amount it can hold is 215 grains at 90 degrees Fahrenheit. All right. The relative humidity is at 46.5%. 100 over 215 gives you a ratio. All right. Same thing again right here. The W max at 75 degrees Fahrenheit is 130 grains. All right. With an actual humidity, your relative humidity is 100 over 130, gives you 76%. And last but not least, W max at 67 degrees, 100 grains of gives you 100, and 100 over 100 is 100%. So basically what you're looking at here is the same amount of water in every single one of these scenarios. If you have 1 pound of dry air with 100 grains of H2O entrapped in it, each one is the same, but it's the ratio that's still important, because that gives you the idea of how much water can be held in that 1 pound of dry air and what you actually have. So even though this scenario over here, if you have scenario 1, 2, and 3, scenario 3, even though you're sitting there with the same amount of water, the same amount entrapped in the air, that is going to feel, you're going to be damp Everything that you touch is going to be damp. It's going to be feeling like you're walking through a rain cloud because you're at 100% humidity. But if you just go over to situation 1, it's the same amount of water. It's the same volume of air. It's still 1 pound of dry air. But because of the temperature increase, that temperature, that dry air, 1 pound of dry air, can hold more water in it. So everything's not going to be damp. It's actually going to be relatively dry out. This would be a very dry 46%. Relatively. This would actually feel pretty okay. It would just be like you would just feel that day's heat. That's the best way to describe what's going on there. And then you have 75 Fahrenheit. Over here in situation 2, same thing again. You have 100 grains of water in 1 pound of dry air. This feeling here, number 2, is like a cool summer day where it's just about to start raining. All the clouds are covered. All right. You're at 76% humidity. You know, it's not that damp out, but it feels like it's going to get ready to rain soon. All right. So if you look at 67, situation 3 that we labeled over here, when it's 100%, 100%, or 100 over 100, that's its dew point. All right. It cannot hold any more water. Before we move forward, has everyone got what I said with those 3 situations? Okay. So this is a psychometric chart. All right. These are important for if you guys are facility engineers, if any of you are, this is not going to be the last time you'll ever see this in your college career. All right. These things become very important on your end. When you guys take thermo, as with mechanicals, you guys will be seeing this, of course, as well. And through your time with any of your Coast Guard licensing, this will play a big part in it as well. So this talks about a huge amount of information. These, for your Coast Guard licensing, is a give me question. It's all right here. It's like earth science with your, those packets they used to give you for all your information. It's all the information's right there. Just got to know how to apply it. All right. So along the bottom on our x-axis, we have dry bulb temperature. All right. And then we have on the y-axis, we have our grains of moisture per pound of dry air. Couple extra things that are just not locked in our X and Y. We have our relative humidity lines. That's these curved lines right here. All right. That's our relative humidity. Our dew point goes across, and it's actually located right at the maximum of each one of these points. And then we have our wet bulb, which goes on a slant horizontally. All right. We're going to go over what our wet bulb is and our dry bulb is in a slide or two. But let's just go with what we know so far. If we have 100 grains of moisture per pound of dry air, that's our W. All right. So it's the same thing of what we just did. Instead of doing a calculation, we can do it this way. All right. And then our dry bulb temperature is at 90. Our W max, if we go all the way up to where our relative humidity is at 100%, because our relative humidity lines are these lines. So we hit our maximum, which is our dew point, and we go across, we see that it's 220. So that's our W max. All right. And right where they cross, that is our relative humidity. That's what we just got in the last slide. Right here, 46.5%. All right. So if we do that again for the next situation, situation 2, that was at 75 degrees out. We know we can find our W max by going up to the 100% humidity line. We go across, we find out that it's 130. And then we can see right there is our next point where they intersect. All right, is where you can find out your relative humidity. So there's 2 ways you can find it out using these charts. You can either watch where they intersect, or you can have what you have is your grains per pound, and then you can go up to your W max, find out your W max, and then divide them, and you can get your relative humidity that way. All right, so there's always 2 ways to go about getting this. And then last but not least is the third situation. That was at 67 or something like that. I forget where it was exactly. You come up, that was at 100 grains, and that's at its dew point is 100% humidity. Okay? Does this chart make sense to everyone? We're going to be using it a lot more. So, you know, if you're not getting this basics, I'll go through it again.
Hold on. So going to W max, and then following that over to the y-axis, that gives you the bottom number that you need to.
Yeah, so that gives you, so your W max is the maximum amount you can hold in that 1 pound of dry air. Okay. And there's a question in the chat with, I will get you. But your W max, that's your maximum allowed. And what's showing here on the chart is that the way you can find it here is that if you go to what temperature you're at, you can choose any of these temperatures, 20 to 110. And if you, well, 110 will be very hard. So let's just stick to 95. And you follow that line straight up all the way to the 100% humidity line. That's your top most line with your relative humidity. That will be at 100% full of water. It can't hold anymore. This part of the chart over here does not exist. You follow that up and you go across to the y-axis and you can find out your maximum amount numerical of how many grains of moisture per pound of dry air that 1 pound of water can hold at that temperature. And the question in the chat was, why are we always using 100 grains? That's to show that you can have the same amount of water in 1 pound of dry air, and you can have different relative humidity at each one of those points in each temperature. And that's going to play a big part in how we control humidity in air conditioning and in heating. Remember, we talked about is that it's air cleanliness, it's air movement, it's humidity and temperature. And what we're going over right now is how we're controlling humidity. Air cleanliness is easy. Do a couple air change outs, slap a filter on the air conditioning unit, you got air cleanliness. Bring in some fresh air. Air movement, it's easy. Control the fan speed of what's pushing through it. This is where it separates a good air conditioning unit and not, is the control of the humidity. Anybody can control air movement. Anybody can slap a filter on something. But this is where everything comes together with humidity and temperature. They go hand in hand with each other. All right. we're not going to be done with this. All right. So do you guys want anything more on this that I can explain as far as what we're going to be doing? The wet bulb we'll get into, the dew point we'll get into more. But as far as how we got to these 3 points, do you guys want more? Another example, a different example? Or are you good? You guys are good? All right. So with wet bulb and dry bulb temperature. So your dry bulb temperature is the actual still air temperature. So the way we can think about with dry bulb is that you take a thermostat and you just sit there and you slap it on a wall or you hold it in your hand. You're not influencing the sensor. So it's reading normal. It's reading what's around you. Okay? That's dry bulb temperature. That's the air fully around us. The wet bulb temperature is determined by a sling psychometer. It's a thermometer with a water-soaked wick around the bulb moved rapidly through the air. So what you're doing is you're almost whipping the water off, and you're trying to use air movement, air speed, to see how much of the water will evaporate. So, like I said, the dry bulb is uninfluenced. That's dry. It's nothing is affecting it. It's a 90-degree day outside. When you hear someone say that, that's a dry bulb temperature. All right. When you have your wet bulb, you have the water-soaked wick, and you're basically slinging this thing around on the end of a rope. So as the water in the wick evaporates because of the air movement that's going through it, the wet bulb temperature is drawn downwards. All right, because think about what we're doing here. We're doing a heat transfer. We are changing the state of water. It's going from a water liquid-soaked rag, and we're trying to evaporate it. We're trying to turn it into a vapor. So as we do that, we're changing and we're removing heat, because this thermostat right here was sitting at 90 degrees Fahrenheit a few seconds ago. And as we spin it around, the spinning is to increase how fast this will happen. And as we go through it, the drier the surrounding air, the greater the difference. So the more water you can evaporate into the air, the drier that air is that day. Because the air, that 1 pound of air that we've been talking about, has the more room in it to take in more water vapor, more grains of water to go into that 1 pound of dry air. Remember, they have a maximum. So if it's a 90-degree day, they might have a maximum of 220 some odd grains. All right. So if we have a wet bulb temperature of like 85, that means it's a pretty humid day. But the farther down this goes, the more and more water has evaporated and left this wick. It didn't fall to the floor. It didn't fall and hit your brother in the face while you're swinging this thing around in the backyard. It went into the atmosphere. All right. So the farther it goes down on the wet bulb, the drier that day is, because there's more room for it to go in. Does that make sense to everybody? So, and last but not least, if you swing that thing around and nothing happens, that means it's 100% humidity day. All right, where the temperature of the wet bulb is equal to the temperature of the dry bulb. Remember, dry bulb is what it is unaffected. Wet bulb is determined by the sling psychometer, and it's just showing how dry of a day that was, how much water has evaporated.
Is it like they start out the same and then you spin one of them and you see how much room there is for water to leave that one and then you compare them?
So yeah, what you're doing is you're when you start out like this experiment, if we can call it. So if you have your dry bulb temperature, when before you even dip this into a water-soaked rag, it's not gonna be sitting at 74 degrees Fahrenheit. It's gonna be sitting at 90. So as you're swinging it around, you're trying to speed up. You're trying to speed up the process. That's what you're doing with just the swinging it around. You're not like trying to like take it like a wet rag and fling the water off of it. What you're trying to do is speed up the evaporation process with moving it through the air. Now you're going about, and it starts at 90, and as you are removing heat and you're removing energy from this thermostat, all that energy is going into evaporating and changing the state of this liquid down here. Okay? And what it's measuring is that energy loss. It's also measuring and giving you a point of reference. Where you started was 90, so you know where you're at with there. And when you go to your wet bulb and it's lower, it's never going to be higher. It's always either lower or equal. What it's giving you is the ability to use that chart to show what your humidity is, all of the other information that we're going to be pulling from it with just these two numbers. All right. And if they're equal to each other, you don't even have to go to the chart, because the temperature of the wet bulb is equal to the temperature of the dry bulb, which means that no water has evaporated, which means that it can't evaporate, because it doesn't mean that there's not enough energy to do it. It means that there is no room for it to even enter the air. Like I said, you can't go above 100% humidity. It's impossible. All right. So this portion will help. Okay, so we just said it was 90 degrees outside, just like just the last slide's example. And we are looking for a number of information, but we can take a look and see that our wet bulb temperature was 74. All right. We drag it straight down. We could see our 74s here. And as we go down that line, where they intersect gives you your relative humidity of 47%. Okay. Other things that you can look at, even with that information, because now all we found was our wet bulb and our dry bulb. We can find out obviously we can always find our dew point as long as we know the dry bulb. All right. We can always find how many grains we're at right now. We can say it's about 100. That's how many grains we would be with 1 pound of dry air. All right. We can find out our actual maximum. All right. And if we go through, we can see other instances as well. So here's another one. Instead of having a wet bulb of 74, we have a wet bulb of 60. We have a 15% relative humidity. We haven't changed our dry bulb. We're only changing our wet bulb in this situation. And then there's a wet bulb of 85. And that gives you a relative humidity of 81%. Okay?
Hold on, so the equation for wet bulb or for the equation for relative humidity was difference between wet bulb and dry bulb, or dry bulb and wet bulb.
It's not the difference. It's the greater the difference. So if you have a 90-degree day of our dry bulb, what you have to think about is their delta. Their delta doesn't mean anything besides, like, it's not going to give you a numerical relative humidity, their delta. What their delta is going to give you is the idea of, okay, I have a big delta. That means I'm going to have a low relative humidity. Okay. If you have a smaller delta, that's going to be a higher relative humidity. Like I said, if you have a delta of 5, that 5 doesn't give you your relative humidity, but that 5 is going to give you the idea of, wow, that's going to be a very humid day kind of thought process. It's going to give you a high relative humidity. Because if we look and we see we have our 90-degree day in our dry bulb temperature and our 3 different wet bulb temperatures, the delta from 90 to 85 is 5. But that doesn't correspond to 81% relative humidity. But it is telling you that you have a high humidity day of 81% because it's a low delta. And if you have a high delta from 90 to 60, that means that a huge amount of water has left the thermostat, and it has gone into the basically it's gone into the air. And you have a 15% relative humidity because you have a large delta. All right. So let's take a break. We're already at this for about an hour. All right. Let's call it let's go call it 10:20. We'll come back to it. All right. I'll see you guys at 10:20.
Mr. Corvo. Wait. Wait, what the hell is that?
Brian, my guy.
The nanobots. I lost speed. Hey, no. Don't listen.
Oh
to
shit,
Hvac.
my
He's
bad, man.
literally a guy.
All right. So I know I asked you guys this during last semester and everything, but so I'm already making changes again for how I'm going to teach 540 next semester. Well, not next semester, but in the spring. But I have we talked about if I gave you guys like valves that were cut in half and stuff like that, you would have appreciated that when we were talking about valves, right? But when we talked about refrigeration yesterday with reefers, would you guys have wanted if I had like an old air conditioner pulled apart, would you guys want to put your hands on that during class? Would that have helped you guys, you think?
Yeah.
Okay. I just want to make sure that you guys think it's not going to obviously be able to help you guys now, but for next semester, next group of kids that are coming through. Because I found one and I'm going to be doing that. I just wanted to make sure I want to put the effort in that you guys think it would be worthwhile. So anybody pull out their fridge yesterday or no? Parents didn't let them? Studying too hard? All right. Everybody here is here, right? Let's get going. So this is called like a primary refrigerant, system where you have your inside temperature. Here's like a brick wall. I'm going to change my color to, let's go purple. Purple seems nice. Yeah. Green. Which one of those shows up better on this slide? Yeah, yellow looks good.
Yellow or green? Or
Right.
yellow.
Yellow?
Yeah.
All right. So we have our inside temperature of 75. We have an outside temperature of 95. Pretty damn hot out of a day. Let's put on the AC. So what does that actually mean? So again, exactly what we would have on a reefer system. You know, you still have your compressor. You still have your condenser. Condenser is outside. That's those big machines that you guys see up on towers and on the side of people's houses, and you hear them click on and everything else like that. Also, fun fact: your compressor is inside of your condenser. If you have a machine on the side of your house, those boxes, and you have that fan blade on the inside, right here. Look inside of it the next time when it's off, and you'll see a black canister. That's the compressor. All right. So your condenser is outside. That's going to be dumping all of your heat, everything that you absorb from the inside to the atmosphere. All right. You still have your TXV and you have your evap, but instead of broccoli trying to be cooled, you're trying to cool everything in your house. And I really mean everything. You know, you gotta, you know, think about it. You have like your stove, your human bodies, you have desk, you know, every object in the house has to be brought down in temperature. That's why when the first time you put on your air conditioning, it feels like it takes so long to reach that temperature, to reach a cool temperature where these air conditioners are on for so long. All right. It's the same effect if you go to the food store, you're having a party that weekend. And so you buy all this food and you stuff your fridge filled with stuff, and you look at your fridge temperature and it's like 64 degrees. And you wake up the next morning and it's finally getting to like 40 degrees. Think how long all night that thing has been running, trying to draw the temperature down. It hasn't reached the temperature it needs to be set at because you're trying to bring everything down in temperature. So you're trying to remove all of that heat. And that's what you're doing with that evap. All right. So these primary refrigerants, what you're doing with these is that you have a mixture. You pull in your inside air and you pull in your outside air. It's going through the fan, and you're basically going through. You get a mixture, and it goes through your evap. It's cooling it down. It gets sucked back in from the inside and from the outside. You get a mixture. Some of it goes this way, some of it goes that way. But what's happening is that you're pulling in air. It's going across your evap. It cools down. It cools down the air in the room. It gets sucked back in, and then it gets reconditioned. All right. That's a primary. But the big concentrate here, and we'll talk about how all the ducting works later into the class. But the primary, you're using the refrigerant to cool the air. All right. In a secondary refrigerant, and the reason we bring both of these up is because our ship has both. A secondary refrigerant unit will keep everything in-house. Like, it'll keep it all in one room. So what you're doing is that you actually will have an air handler that will be physically cooling the air. But your refrigerant will stay in this one space with your air handler using like chill water to circulate through your evap and back out into your air handler. So your air handler is like your glycol. All right. That's the one that's actually doing the cooling. That's the one that's removing the heat of the room. Whereas with your evap, which is called a chiller in this situation, is removing the heat from the chill water. All right. So that's a secondary refrigerant. Does those two versions make sense?
What was the big difference? The secondary has an air handler.
So they would both technically have an air handler, but the big difference is what is actually cooling down the air of the room. All right. Wherein a secondary refrigerant is using a chill water cycle where it's basically just like a chill water loop. It doesn't have any ability to heat or anything like that. All it's doing is going into the evap and coming out cold. All right. So a good example of this would be like
And what is the primary?
Brandon, you were breaking up like crazy.
I know internet sucks right now. So, what's the primary
So
to cool everything?
the primary is using an evap. So you would be blowing air over the evap. All right. Whereas with a secondary, you're blowing air over a chill water line that is getting cooled by the evap, but the actual air going through and into the house or into the space is going through and being cooled by a chill water. That's a secondary. Where with a primary loop, the evap is cooling the air. A way to think about this is that if you had, if we talk like redneck engineering here, if you had a bucket full of ice, all right, and people have seen these things before where you can it's a bucket full of ice, you poke some holes in the bottom, and you throw a fan on top of it, and you're cooling down your space. Yeah, it's probably cooling down your space, but so all the air getting sucked in through the bottom, going by the actual cooled ice cubes in that bucket of ice and being blown out. That would be like a primary refrigerant. You're using the ice directly to cool the air. But if you wanted to go into some advanced redneck engineering, where instead of cutting some holes into the bottom because that drains out and makes a mess, what you do instead is you get a box fan and you get some copper piping and you lay some copper piping on the box fan and you get a fish pump and you basically make your own little chill water pump. So you run a loop inside of that bucket of ice, you're no longer making a mess, but that would be a secondary because the water that's going through and into that fan is going to be cooled by the ice in the bucket. But the actual cooling means is done by that cool water that's going through those copper pipes over the fan. That's the two levels of what we're looking at, is what is physically cooling the air that's going to be in the space. All right. So let's talk about air handlers. You'll have air handlers in both versions, primary and secondary, okay? But really what's happening in them is what they sound like. They're handling the air of that space, all right? So you have your exhaust fans, all right? Ooh, yellow is not going to do well on this page. Yeah, that's better. So we have from our accommodation space, all right? We have a fan that's going to be drawing that in. Now, we have a couple of things that we need to take care of with HVAC, right? We have our air filter. So that's taking care of our air quality. We have our fans. Our fan in and our fan out, that's taking care of our air speed. It's a nice speed. Everyone's happy. But all we're doing right now is just kind of filtering the air with 2 fans. So we also need quality taken care of. So that's when we open up and we have our actual how much fresh air we're going to be getting. Because if you just keep breathing, you're going to run out of oxygen eventually. So in this situation, 100% is recirculating. What's getting sucked in from the space is going back into the space. It's just getting filtered. In this situation that we come into, it's 100% going outside. So 0% recirculating, 100% fresh. All right. So this is our fresh air over here. And this is just vent into atmosphere. Now, neither one of those are good scenarios to be in. Okay. Now, when you see, this is a thing that drives me up a wall. When you have in your car, you have a little symbol that kind of like looks like this, where if like a vehicle and everything, it's usually on your fan speed and everything else like that. And it's really just an arrow showing a recirc back into your car. What scenario would that be in? It's a terrible picture, by the way.
100% recirculation instead of.
Yeah. That button is just 100%. It's in a situation where, you know, you're going to be going through a job site where it's really, really dusty. You know, or if you're on a dirt road and you don't want that air to be going through and clogging up if you have a, you know, cabin air filter or what have you. People use it for smells if you're going through like a crazy long construction. I know we don't see that much in New York, but when you get out into the country, it's there's miles and miles of construction that they'll be doing. So sometimes you'll be in areas where you need recirculating your own air in your vehicle, so that way you don't get that construction smell into your own car. It's a nice effect. Same thing with anything with air conditioning. But that button does not turn on your compressor, as some people like to believe. All right. So most people, when they're running air conditioning in places, they want a little bit to be exhausting and they want a little bit of fresh air to come in. Not too much of either, because think about how much energy you're going to be dumping out into the atmosphere. You put all that energy into air conditioning. Why dump it to atmosphere? You know? And why do you want to draw in so much humid air? You have to take care of that air now. But you want enough to keep it fresh. Let's go through the next. So let's talk about summer operation. And we're going to be talking about, like we said, HVAC takes care of, you know, heating and cooling of spaces. It's comfort. So talking about summer operation, what we see is we have 78 degrees Fahrenheit coming back from the accommodation space. This air it's heated up because it's drawn out all of the warmth out of people's bodies, out of what the fridge has been dumping into it, computers, you know, anything that's been putting out heat into the spaces, heated the air up to 78 degrees. So it goes through this whole piece. Some of it goes out. We have 95-degree day coming in. So they mix and we get 85-degree Fahrenheit before it even starts to be air conditioned, quote unquote. All right, we have a 60% relative humidity. That can be coming from people breathing. That can be coming from the outside. It could be a humid day. All right, so we have a 60% relative humidity. Goes through the air filter, takes care of the pollen. We're clean now. And now we're using a chill water loop. All right, so that chill water is going to cool that air from 85 degrees Fahrenheit, 60% relative humidity, down to 50%, 50 degrees Fahrenheit, and 100% relative humidity. And that's the biggest thing that we're seeing right here. We have dropped the temperature for one main reason, and that is to control the humidity. We're not going to be putting 50-degree Fahrenheit air into the space. That would be freezing. And we're not going to be putting 50-degree Fahrenheit, 100% relative humidity air into the space, because everything would just be damp. And this would just be the weirdest air conditioner. It wouldn't work. No one would want this. You would be a terrible business owner if you try to push this on people. So what we need to do is we need to reheat the air, because what we, like we talked about, relative humidity is the ratio between how much moisture you can hold and how much moisture you have. So if we're at 100%, that means that we are completely packed with moisture. So what we're doing here is we're dropping our temperature, because if we remember that 100% curve, the higher you are in the temperature, the more grains you can handle. But if you drop it down to here, if you go from 85 down to 50, instead of having 100 grains, remember, you have to sit on that moisture line. You can't go above 100%. So when you drop your temperature all the way down, as soon as you hit that 100% relative humidity, you can hit it at, say even at 80. As soon as you hit that dew point where you're at 100% and you're still falling down on that curve and you're still bringing your temperature down, what you're doing is you're driving out any of the water that's in the air, because you can't go above 100%. So instead of having 100 grains of water in the air, you're going to have 90 grains of water in the air, but you're at 100% humidity still. And you drop another 5 degrees. You're now at 75 degrees. So instead of having 95 grains of moisture in the air, you're now down to 90, but you're still at 100% humidity. And you're dropping all of that water in the air. You're trying to make it fall out of the air. Does that make sense? Okay. So again, we're not going to leave it at 100% humidity. That would be terribly uncomfortable. So we need to reheat it. So all we're going to be doing is just reheating it to a point where we want it to be at and where we know where the relative humidity will be comfortable. Okay. So let's look at that whole thing that we just saw. This is where we started. This is where we were coming in to the filter. All right. 85 degrees, 60% relative humidity. Let's change this to yellow. Look good on there, or go back to red on this? We'll do red. So we go across and we can see our dew point is at 68 degrees. All right. So this is what's happening here. We started out pre-filter at 85 degrees Fahrenheit and 60% relative humidity. Now, as we drive across on this x-axis, we are not changing how much water we have in that 1 pound of dry air. It has not changed until we hit 68. And at 68 degrees, we have now hit our dew point, which means anything lower than 68 degrees, moisture is going to start falling out of the air because it cannot have that moisture in its air. So as it falls down this curve and goes this direction now, we are staying at our 100% relative humidity line. And that's where we end up at this 50 degrees, 100% relative humidity. Okay. Now, instead of having 110 grains per pound, we were having 55 grains at 50 degrees. So we want to end up somewhere in here. Like we talked about, everyone's about 68 degrees. No, I'm sorry. We wanted, that's winter operation. We want summer operation. We want somewhere around in this region, depending. So let's call it like in the 75, wherever we're going to be pumping that air out, we are going to be having a relative humidity of somewhere in here in that blue box. So this is our reheating, this dotted line. All right, because we cannot remove any more moisture. unless we drop the temperature more, but we don't want to. All right, we're at a relative humidity that we will like. So all we need to do is just increase our temperature. The humidity will stay the same. The amount of grains will stay the same. And our relative humidity will drop, and everyone's all happy. We have taken care of humidity and temperature together. All right, that's what's happening inside of an air handler like this. So that was summer operation. If we go into winter operation, things change a little bit. So instead of having a hot space that we're trying to cool, we're trying to heat a cool space. So from our accommodation, 68 degrees Fahrenheit, we're still going through an exhaust fan. Nothing has changed, except for the fact that we have 5 degrees here. So we have a 40 degree instead of a closer temperature. So this is one way we're going to be having this. We have a preheater and we have a reheater. And what we're doing is, instead of taking away humidity, we're adding. We're going to be pumping in and almost spraying and spritzing, aerosolizing moisture into the air and trying to increase our humidity. You know, we don't want to dry heat in the house. Everyone's skin cracks and it's just uncomfortable. You feel like it's not, when you're in a hot area, but it's dry, you just feel very hard on your body. All right. And again, no one makes any money from air conditioning when it's running. It's not like you can put produce in it and sell it to anybody. This is all comfort. We want to take care of ourselves. I'm sure if they would find a way to spritz lotion into it that would lotion your skin, I'm sure they would do it. So this way of what we're doing is not the best way, and we'll show about it in a second, because we have a preheater, then it goes into our humidity, and then we're reheating it again. All right, we're heating it twice so that way we can take care of our humidity as well. So we have a nice humidity going to our accommodation space at 65 degrees. So the better scenario, and because we don't want to be changing a lot of, we want to be using the same air handler. What we have here is our chill water. That's what normally would be in that spot. So we can't put the preheater there. So the preheater would be in this space, heating the air that would be coming in from outside. So you would have a higher temperature before it even hits the filter. That's what you're trying to do. All right. Remember, you're trying to make everything fit in a small footprint. So these are terminal reheat systems we'll talk about here. We have our exhaust, we have our recirculations, and we have our fresh air. All right, these gray pieces right here are fans. I'm going to go back to yellow. And our exhaust right here, this is going back outside. Our fresh is coming from outside, all right? And this is recirculating. This is coming from space. So we have our preheat, we have our cool, and then we have our reheat, and we're going into a zone, all right? So this is going to be controlling particular zones. If you're in an office space, you're one of the head honchos, and you want to have, your office set at a different temperature than, it's cold outside. You want to be warm, but your employees shouldn't be that warm. That costs money. So that's what we would be doing here with controlling temperature. So you would use a heater. That's a terrible color for this. You would use a heater particular at their station. all right, you would be heating to the temperature of the room, of the set point that you want in each individual room, using these heaters that are set at their spots. So you'd send out a general temperature that would work mostly for everyone, and then you can heat it up to a certain temperature. All right, that's going to be a terminal reheat system. Now, this is a variable air volume system. Same thing again. Oops. There we go. So with this system, what they're doing is they're controlling the amount of airflow that will go into the zone. So the temperature is higher leaving the system, and there's no heaters, but what it's using is how much air comes in to the system at a time. Okay? That's the two ways we can be utilizing this. All right. That's going to be it. Do you guys have any questions or anything that you'd like to go over before we end? You guys feeling good? Because that's all the material that you're going to need for Thursday's test. All right. Tomorrow is going to be review, and then it's a test come Thursday. All right. So come with questions for tomorrow. Come with topics you want to go over. And come with, make sure you guys study so that way we can take care of what we need to take care of tomorrow. So that way, if you have any problems, we'll go from take care of that. And then there's one question in the chat that says, if 70 Fahrenheit output, how can we have the first room at 72? Basically, it's all depending on if that was a summer or winter operation. So that could have been, let's call it a summer operation, because that's probably what it would have been like. If you wanted the room to be set at 72, you would use 70-degree temperature to cool it down. So if it goes above 72, then if it's at 73, 74, you would use 70-degree temperature to bring that room down into a 72-degree set point. It wouldn't obviously work in a winter scenario. All right. Other than that, does anybody have any questions? All right. From my point of view, you guys are good.
Have a good day, Professor.
See you guys tomorrow. If you guys have any questions, I'll stick around, or we can open up a new chat. Everybody good? Brian, you good? Kevin? Nicholas?